So regardless of the type of concentration we're doing, of the three, the amount, the percent, the parts per, we're always using this same format. Okay. We're going to have some quantity of solute on the top, and we're going to have quantity of solution on the bottom. Okay. Previously, an amount, it was moles on the top and volume on the bottom. Okay. And we're just going to play with what units we use as we go through the methods. So the first percent we're going to look at is using volume units on the top and volume units on the bottom. So the top is going to be the volume of solutes. You're going to use this when you have an aqueous solute. Okay? We'll see vinegar come up in some questions. When you make a vinegar solution, you put ethanoic acid, which happens to be a liquid, into water. Okay? So the solute's a liquid, the total solution's a liquid, so it makes sense to use these type of units. Notice the denominator isn't the solute, it's the total solution. Okay? So watch that in questions. If they give you the solute and the solvent, you have to add them together. And I'll do a couple examples like that. Okay? But most of the time in your questions, they're going to give you the total solution volume. We have a lot of glassware that's designed to do total amount of solution. So a volumetric flask is an example of a piece of glassware that holds a certain volume. Okay. This is a 100 ml volumetric flask. Okay. So you can dump a whole bunch of things into a volumetric flask and it just tells you the total. So if we're not getting into a question, we're just kind of getting comfortable with the wording. If you did have a 5% volume to volume ethanol solution, okay, the 5%, okay, we can think of it as 5 parts of ethanol per 100. Okay. So to make up that 100, 5 of the parts, and maybe we'll use milliliters, 5 of the milliliters would be ethanol, the other 95 must be coming from our solvent. Okay. So it's not 5 parts ethanol, 100 water, 5 parts ethanol in a total. To be consistent, 5 parts in 100, or if you switch to milliliters, 5 mils in 100. Now, when you use volume to volume ratios, you can use any units you want, any volume units. You just have to be consistent. They're going to cancel. When you do a percentage, the top units and the bottom units match. So use milliliters and milliliters, or liters and liters, or kiloliters and kiloliters. As long as the two are the same, you're fine. There'll be no units in your answer. So jumping into an example, what is the volume to volume concentration? We have 1.25 mils of ethanol, so it's a slightly different chemical than the one I had in the previous example. It's not a typo. It is Al at the end, put into a little over 46 mils of octane. So anytime you see a percent, you're thinking of getting a ratio out, just like you do on a test. How many points did I get? Divide by the total. We're going to have to do the same thing. After you get that ratio set up, because it is a percent, you're going to multiply by 100. So the solute goes on the top. So we have to kind of figure out or guess. Typically, the lower amount chemical is our solute. That's what I'm inferring from this data. So I have 1.25 mils of the lower amount chemical, assuming that's the solute. Once I put milliliters in the top, I am forced to use milliliters in the bottom. Okay. I have matching units in this question, but you know you're going to see ones where they don't match. You might get milliliters of solute, liters of total solution, and you're going to have to find a common unit. Okay. Either common unit, milliliters or liters, will work. Okay. So do we know the total volume here? We actually don't. We're given the solute and the solvent. So to get the total solution, I'm going to add the two together. Okay. And this is going to be a pretty reasonable estimate of the total volume, 47.47 mils. Now, when you mix solutions, you don't always get exactly the addition of the two volumes. Sometimes the mixing changes the density, okay? But I'm assuming that these two volumes you can just straight up add. So 47.47 mils. We end up with no units whatsoever. And I get 2 point, and then I think of how many digits I want to write. When we added the volumes, we tracked hundredths place, which gave me 4 significant figures, but I only had 3 significant figures in the solute. So 2.63% volume to volume. Sometimes consumer packaged goods will have the V to V, other times they just put the percent and they drop it. Okay. So that's our first example. Again, most of the time in questions, don't always just start adding the two volumes. Watch to see if it said total or did it say solute. So that's a volume to volume example. You can also do this with mass. So this is done typically when the solute is a mass and the solvent is a mass, or the solute is a mass and you're putting it in water, and you can just weigh the water or weigh the total mass of the solution easily. Okay. So we're just leaving milliliters to milliliters and probably going gram divided by gram, or potentially kilogram over kilogram. So 10.1 grams of sodium chloride, so salt, is added to 325 mils of water. So that's not the total amount. We're putting the two together again. And what is the weight to weight percent? So again, soon as you see percent, solute, divide by total, times 100. Here, it's always the ionic compound that gets broken up in water. So we really know for sure that that is the solute, 10.1 grams. Now we need the total mass on the bottom, but we have milliliters of water. Now we're going to do a mass to volume conversion in Chem 30. We do this a lot. You're going to start doing it in Chem 20. We don't need to weigh water. 1 milliliter of water is equivalent to 1 gram. I'm not using equal, I'm using equivalent to. They're exactly, okay? That's not 1 sig fig there. 1 milliliter is 1 gram. So this 325 mils is 325 grams. We can only do this with water. But many times in the lab, you're going to use a graduated cylinder. You'll measure out a milliliters of water, and in your lab book, you'll have to convert it to a mass. So what's our total mass? We have 325 grams plus 10.1 grams. Okay. Now, if you throw this into your calculator or just add this up, you're going to get 335.1 grams. And we don't want to round early, so we can use all of those digits. Okay? But if you think in terms of significant figures, we know to the ones place in the first measurement, but we know to the tenths in the second. Okay? We do not know this digit. Okay? So from a science perspective, not a pure math perspective, this one we don't really know, because that is coming from a I don't know plus a 1. Okay? So we leave all the digits, but this is why sig fig wise we only have 1, 2, 3 known digits. We don't really know that one. We're unsure what the unknown measurement was there. So even though I wrote 4 digits there, there's only 1, 2, 3 sig figs. The top is 3 sig figs, so I'm going to round to 3 significant figures when I carry out this math. Okay? So when we add or subtract, we track decimal places. The number of sig figs we'll round to at the end is coming from, or the decimal places come from the least place. In this case, it's the ones place that's common to both. So that was the last digit I would count as a significant one. Okay? But again, you always leave them all in your calculator till the end. So grams over grams cancel, and I get 3.01%, and this is a weight to weight. Okay? So my first 2 examples, they're a little bit uncommon where I had to add the solute and the solvent, but I wanted to show you that for that odd example where you have to add them. It's easier if they say total solution, total mass, you plug that right into your denominator and you don't have to do any extra work. So the first couple examples have been determining percentages. My last example on this slide is going to be using a percentage. So think of this as part A. This bottom question, I'm labeling it as part B because the data above still applies. So we have this 3% weight-to-weight solution, and how much of this solution would we need if we wanted 1.2 grams of solute? It'd be buried in the solution, but we only want 1.2 grams. So whenever I have to use the concentration, whether it's a percent here or part per million, part per billion later, the first thing I'm going to do is take the percent and kind of undo it, or take the concentration and turn it back into a ratio. Okay. That ratio is going to be solute divided by total. Solute will go on the top. Our total solution will go on the bottom. If I take that ratio and then I multiply by our solution volume or solution mass, that's going to equal my solute. So it's just one way that you can organize these and solve them. Okay? So I'm going to take my concentration, turn it back into a ratio, undo the percentage. You know how to undo percentages, you turn them into a decimal form. Okay? Multiply by solution equals solute. Depending on the question, this might be the unknown, or that might be the unknown, and you just rearrange and solve it. So that's going to be my consistent format. So let's take those question marks out and start filling in the data for this question. So how much solution would be required? So that is the question mark, or maybe you'd probably put an X in its place because you're most comfortable solving for X. would be required if a total of 1.2 grams of sodium chloride was required. So that's our solute. Okay. And we're going to need to get that original ratio back from our percent. Okay. So to undo a percent to turn it into a ratio, you just divide it by 100. So we have 3.01 out of 100. Okay, that's the decimal form. I just haven't actually done the divide by 100 yet. Okay, and then we can put back any units we want. Okay, we just think of the type of question we're dealing with. This is a weight to weight, so I have to use mass. I can pick any mass units I want, and I want to make my life easy for myself, so I'm going to pick grams because that's what's already in the question. So 3.01% is like 3.01 grams out of 100 grams. Okay. When you undo the concentration, you get to pick any units. And now I have things nicely set up. I can rearrange and solve for that question mark. So the question mark equals, I have to pull this ratio to the other side, and when I do, it ends up flipping. So 1.2 grams of solute times 100 goes to the top. The 3.01 flips to the bottom. So I'm skipping my algebra or the math. Okay. So I rearranged this all in my head, wrote it in one step. We have grams in there 3 times. The top numerator and denominator cancel, but grams is our final unit. And I rounded this to 2 significant figures. So we had 1.2 grams, 2 sig figs. Okay. I ended up rounding it to 40, which is a little ambiguous. If you want to be less ambiguous, you could use scientific notation, or you could use switch the units. Okay. 4.0 times 10 to the 1 grams would convey the sig figs. Okay. So this is one method that you can use to solve this. Okay. You come up with another method, that's fine, but this is going to be mine. Okay. So that's 2 examples. We've been through 2 of the 3, volume to volume, mass per mass. We're just going to look at this mass per volume and how do you decide your units when you're using a mass or a weight in one circumstance and you're using the volume in the next. There's a very distinctive way we have to do it. Okay. So concentration, mass per volume. Now, most solutions are water-based. So what I mentioned, we're just going to do water-based mass per volume examples, and we're going to pick kind of equivalent units for water. So if we want to use grams on the top, we're going to use the milliliters that's equivalent, or the volume units that's equivalent to grams. So for water, grams and milliliters are kind of equivalent to each other. Whether you say 1 milliliter or 1 gram, they're equivalent. So you can use that pairing. Or if you multiply everything by 1,000, okay, 1,000 grams is a kilogram. And what's 1,000 milliliters? That's 1 liter. Okay, so you can use either version. Okay, grams of solute to milliliters or kilograms to liters. Okay, and again, this just holds true for water or water-based solutions. Okay. So we have a 5.0 weight to volume solution of acetic acid. Okay. This is vinegar. You go to the grocery store, that's the most common concentration. Okay. If you bought 25% vinegar, it would be pungent. It would be strong. Okay. So when you buy vinegar, it's actually mostly water. The grocery store is not going to put moles per liter. My parents would have no clue. If they went to the grocery store to buy vinegar and it said moles per liter, they'd be pretty lost. Just they don't have that science background. They don't understand moles. But pretty much everybody can understand percent. You know, they know 50% is half, 25% is a quarter, 10% is 1 in 10. Okay, it's something that people can understand and appreciate. Okay. So if you put 25 milliliters of vinegar on your French fries, how much pure acid did you just put on your fries is essentially this question. How much solute is in 25 mils? Okay. So we're using a percent. So I'm going to do that same layout I just did. I'm going to turn the percent into a ratio. I'm going to multiply by total solution, and that's going to give me the solute. So we have a 5% weight to volume. So 5% is 5 parts out of 100. I'm going to keep filling in before I go back and decide, do I want to use grams and milliliters or kilograms and liters? I can pick either. Total solution, we know that, okay? 25 milliliters. And they're asking us, what's the mass of acetic acid? That's the solute. That's what we want to get. So instead of a question mark, I'll put an X in. So we have milliliters of solution, so I want to use grams and milliliters. If I can make my units match, I won't have any conversions to worry about at the end. So 5 grams out of 100 mils is 5%, 25 mils. And our solute is all by itself. There's nothing to rearrange here. Okay. I've set this up that the units of solution match the units in our ratio. So all that's left is grams. So the X, we have grams, 5 times 25 divided by 100. Hopefully you don't even grab your calculator for that, or you start doing some of it. 5 times 25 is 125 over 100. Okay. But then you have to round it to 2 sig figs. So I rounded the 1.25 up to 1.3 for the sake of sig figs. So 125 divided by 100 and then rounded. So when you put 25 milliliters of vinegar on your French fries, there's a little over a gram of pure acid. It's a weak acid, and that's why it doesn't kill you and isn't harmful, but there's a little over a gram of acid.